At this point, I would like to discuss the law of total probability once again. As I said in class before, it's a very important concept, the law of total probability, and we discussed this with respect to a partition in the computation of the probability of an event, let's say A. Here you see the statement of the law of total probability for a partition B1 through Bn. To compute the probability of an event A, we just condition it on each of these events and used uh, the definition of conditional probability to write this. And this we can apply to PMFs and CDFs. Why? Because PMF and CDF are defined in terms of probabilities. You see, this is the probability that x equals x, and this equals the probability that x is less than or equal to x. Okay, so these are events at the end of the day. These are probabilities of events. So we can just use law of total probability to write the PMF or the CDF of a random variable. Okay, here we will have the PMF conditioned on each of these events, B1 through Bn, multiplied by their individual probabilities. This is direct application of the law of total probability. Similarly with the CDF, you can obtain the CDF by conditioning this on each of these events. As we have seen earlier, this is useful when you cannot write the PMF or CDF directly or this probability directly, but it is easier to write when you condition it on a certain partition of the sample space. It's the same with these distributions. Sometimes writing the distribution outright may not be straightforward, but it might be easier when you condition it on some event. And this here, the conditional CDF, of course, if you differentiate both sides with respect to x, what you get is an expression for the PDF expressed as a law of total probability. Okay, so here we have conditional PDFs weighted by the probabilities of these events in the partition. Okay. Now, consider this partition here, B1, B2 up to Bn. Okay, we say that this is a partition of the sample space, but now let's define a random variable y to represent this partition. Okay, so it will be a discrete random variable here in the first scenario. We will just say that when the outcome falls in B1, we will say that y takes the value of 1. If the outcome falls in B2, we will say that y takes the value of 2, and so on. Okay, so we just represent the partition using a random variable, nothing new here. And we can just write the same formulas we have seen here, these three formulas, using, instead of b's, using the new random variable y, because you see each probability here, this one and this one and this one, these will correspond to the PMF values of y, PMF value of y at k. Okay, so this is much more useful in case you can write maybe you cannot write the distribution of a random variable directly, but it's easier to write it when you condition it on some other random variable. Okay, so this is how you can relate the distributions and then derive one in terms of the other. And if you actually take this to the extreme, so that this, for instance, represents all elements in the real line, okay? In fact, this can represent each individual real number that a continuous random variable can take. Let's take it to the extreme, and random variable becomes a continuous distribution, okay? And each of these B1, B2, now they will go up to B infinity, because you will have an infinitely many real values, and they represent each different outcome that the random variable y can take. And here I'm going to write this as the law of total probability for continuous distributions. For any event, you can now write probability of A equals Here, instead of a summation, you see we have an integration because now it's on the real line. So we can represent this using, rather than a summation, a discrete summation, we should have a continuous integration. Probability of A conditioned on the exact value of y equals parameter y, multiply by the corresponding likelihood, let's say the PDF value of y at that point, integrated over the entire real line.